Hi everyone, I'm Gabriel Radan and I'm going to present our work on search by types in libraries and how to make it scale. This is joint work with Clément Alain and Laure Godin. Every programmer has encountered this problem once before. You're looking for a function, you know what it should do. For example, you want to convert some time to a different time zone, but you're not sure where to find it and what's its name. There is an intuitive approach to this. You want a function on time, so you're going to look in the module named time. Unfortunately, it doesn't always work. The function could be in the date module or in the time zone module or something else. There is an alternative approach to this. Behavior are hard to search for, but there are abstraction of the behaviors that we can search for. And in particular, there is a very familiar abstraction for us, the type of the function. And so we've built a tool called Dowsing, which allows to find function by their types. For example, here I'm searching for a function with a type alpha list.alpha arrow pool. And it's going to find the function list.mem with slightly different type, but very similar. Here the arguments are just reversed and then it's curified instead of uncurified. And so our procedure search find types up to order of argument, instantiation of variables, and names, and so on and so forth. It knows about packages and libraries, and in particular it scales to modern ecosystems. So for example, we can search all of OPA. There are several existing approaches to this problem. The first is search by type modulo isomorphism, which we will describe in more detail later. The good thing is that it's sound and complete, which means that we will find types and functions that actually correspond to the query we entered, and we are going to find all of them. The problem is that it's very computationally intensive to the point that it doesn't scale at all to big modern ecosystem. Another alternative approach, which is very popular in the SQL community, is Hugel. The problem is that Hugel is neither sound nor complete. It's more akin to a text search in types. It doesn't really understand the semantic of types, but it scales very well, and it works on the whole Haskell ecosystem. So what's search by type modulo isomorphism? Given a type tau, it finds all functions in the libraries with types which are equivalent to tau in some capacity, either equivalent, matching, or unifying, and with a set of simplification, which we call isomorphism. And here we will choose this for isomorphisms. First, we're going to consider tuple as commutative and associative. We're going to consider unit as the neutral element on tuples. And finally, we will consider types up to curification. So here it takes tuple A, B and returns C, or A returns B, returns C. And those two types are considered equivalent here. The problem is that with these isomorphisms, unification and matching are very expensive, so matching is NP-complete and unification is p-space for two types. So we can't use directly this procedure for an exhaustive search. So what can we do? First, some remarks. When searching, many types do not match. This is expected since if you're looking for a query, there are lots of types which are not related to it. The problem comes with the second point, which is that when failing, unification is still very expensive. And finally, a third point is that performance of unification highly depends on the types. And there are some types, which are not necessarily the big types, which cost a lot to unify with, or to attempt to unify with. So, given this constraint, we've devised a methodology for our work, which is first to experimentally measure to identify types taking lots of time. We then introduce shortcuts to try to skip unification for these expensive types, trying to decide quickly without resorting to the full unification procedure. Then we pre-process the database of types to compute these shortcuts in advance. And finally, we repeat the process until we've exhausted all the bottlenecks. Here is an example of metric, the head. So the head of a type is the nature of the right-hand side. So here the head of unit to alpha is variable. The head of int to list of alpha is the constructor list. We can ask our tool to do statistics when we search for a type. So here int to int, and we classify the time, the resulting time and number of unification by head. So here are all the unification for variables, here for constructor, and so on and so forth. Here we can see that a very large majority, 95% of the types are done, do not have a variable at the head, but types with a variable at the head take lots of time, much more than the others. So our goal here is going to try to classify the head to avoid the cases that are pathological. And we can do so because if two heads are not compatible, then the type will never unify. So we can pre-compute the heads for all types and store them compactly in order to do this very efficiently. And if we do a search in a local installation of OPAM on my computer, so around 250 packages and 31,000 functions, we can see that we avoid making lots of unification. So the percentage here is the percentage of unifications that were avoided by this shortcut. And we can see we avoid many unification, except in the case where the query itself has a variable at the beginning. In this case, we do not gain anything. So we correctly avoided many unification in the cases that are not too polymorphic, but we need to work more for polymorphic cases. And so we have introduced more shortcuts like this, in particular some that are better at polymorphic queries. In particular, the number of variables at the tail of the function is pretty good at this. It allows to classify polymorphic functions by how polymorphic they are, and we can cut them. And we plan to investigate and add more of these shortcuts. And now we have many shortcuts. How do we combine them? So to combine them, we use a trie-like structure of features. So the head is a feature. And we given a query, here, for example, we have a constructor called f. We can select all the subtries with potentially valid types. So a constructor f will never match a tuple. So we can just cut all the tuples directly, and we can cut the subtries containing tuples and only consider the subtries that interest us. And we can stack those trie, and that's how we combine them. So with all the features we've gathered so far, we can do a benchmark, which is presented here, on a database containing containers, batteries, and bays, which represent quite a lot of functions already, 10,000 functions. And we can see that on many of these queries, we obtain times that are less than a millisecond, so under what a human would consider instant. And for more polymorphic types, then it takes more time, but it's still very quick. And so in practice on simple queries, it already works very well. And we can work more on very polymorphic queries. So to conclude, we presented Dowsing, a new approach to search in libraries by types. It is sound and complete, and we've formalized our unification procedure, how our shortcuts, and proved the soundness of the shortcuts. With our method scales to medium ecosystems, and we hope beyond with additional work. And in particular, the most important bit is that we now have a good methodological approach to improve this further by measuring the bottlenecks and finding new shortcuts from them. And so everything is formalized and implemented. You can look at it on GitHub. But there are still lots of work to be done. to make this practical and to develop it up until it's an actual usable tool by the OCaml community in particular. And so on the indexing front, we hope to add more features and to invent new kinds of shortcuts to make it even faster. On the type system aspect, we need to add more OCaml feature. So far it supports basically the SML fragment of OCaml, which is fairly limited. And there is lots of software development work as well, in particular if we want to plug this into the OpenCI and develop the web frontend and have a database that serves queries for the whole of the open ecosystem. And so if you're interested in this, please reach to us, and I hope we can make this an actual tool that will be very good for the OCaml community. Thank you very much.